Okay, so what do a heavy school mag, a sharp knife, and a massive cyclone all have in common? I know it sounds like the start of a bad joke, but the answer is actually this: single invisible force. A force that, believe it or not, shapes pretty much everything around us. We're going to dive into the secrets of this force, which is, you guessed it, pressure. So let's treat this like we're detectives, okay? We're going to start with a few simple puzzles. Really simple stuff. These are things you've probably seen a million times and just never really stopped to think, why does it actually work that way? All right, mystery number one. Think about this. You pack a bag, right? For school, for a trip, whatever. You know how much stuff is in there. You know what it weighs. But for some reason, some bags just dig into your shoulder and feel way, way heavier. What is going on there? And puzzle number two, this one is so obvious we just take it for granted. You take a nail, you hit the pointy end with a hammer, and thwack, it goes right into the wood. But what if you flipped it around, hit the flathead with the exact same force, and you just get a loud noise and maybe a little dent in the wood? It's the same nail, the same hammer, the same swing. So what gives? And our last puzzle, oh man, this one is just pure frustration. Have you ever tried to cut a tomato with a dull knife? It's the worst. You just push and end up with a squashed, sad mess. But then you grab a sharp knife and it glides through like butter. It's the same motion, but the result is completely different. It's all about how that force is used. All right, to crack this whole case wide open, we've got to go back to that first clue. So let's investigate the curious case of the heavy bag. Okay, so meet Mega and Poan. Now, their bags are filled with the exact same stuff, so they weigh the exact same amount. That means the same downward force is pushing on their shoulders. But look, Poan is clearly uncomfortable. He's struggling. Mega, on the other hand, looks totally fine. How can that be? And here it is, the big clue. Just look closely at their bags. See that? Pawan's bag has these really thin, narrow straps. Mega's? Hers are nice and wide. And that tiny little difference, well, that's the key to this whole thing. You see, it's not just about how much force there is. It's about how that force is spread out. For Pawan, that whole weight is focused on a tiny little area, just digging in. But for Mega, that exact same weight is distributed over a much bigger area thanks to those wide straps. And that makes all the difference in the world. And this isn't just about backpacks. We see this idea everywhere. You know how people who carry heavy things on their heads often use a rolled-up piece of cloth? That's not just for padding. It's a super smart way to increase the surface area, to spread out that load and make it way more manageable. So what Mega's bag and that coiled cloth are both doing is actually playing with a basic rule of physics. It's time to name our main suspect in this mystery. That heavy bag, the nail, the sharp knife. Believe it or not, they all come down to one simple, elegant idea that ties force and area together. And that idea is pressure. That's it. All pressure is the amount of force you use divided by the area you're pushing on. Force divided by area. That simple little formula is the key that unlocks all of our puzzles. So here's the absolute most important thing to remember, the big takeaway. If you make the area smaller, the pressure gets bigger, way bigger. You can use the exact same amount of force, but if you shrink the area, that pressure just shoots up. They're opposites. Okay, so let's circle back to our other mysteries. The nail's point? It has a super, super tiny area. So when you hit it, you create a ton of pressure, enough to blast right through wood. Same with the knife. The sharp edge concentrates all your force onto this teeny tiny line, and that's what lets you slice the apple. High pressure is the secret ingredient. Okay, so case closed for solid objects, right? But hold on, we're not done. What about liquids? Does this whole pressure thing work for water too? Well, you probably guessed it, but the answer is a big yes. And you actually see proof of it all the time. It's the exact same rule, it's just showing up in a different way. For example, ever wonder why big water tanks are always way up high, like on rooftops or their own tall towers? It's not so they can get a nice view. Nope, it's a very specific engineering decision, and it's all about liquid pressure. Let's just walk through the logic here. Putting the tank up high creates this long, tall column of water in the pipes below it. All that water has weight, and that weight pushes down, creating pressure. So the taller the column of water, the more weight, and the higher the pressure. And that high pressure is what gives you that nice, powerful stream of water when you turn on your faucet. This little experiment is great because it really drives home a super important point. Look at how both balloons are stretched out the same amount, right? Even though that container on the right clearly has more water in it. So why are they equal? Because the height or depth of the water is the same in both. And with liquids, that's what matters. It's all about the depth, not how much water there is in total. Okay, so we've connected a simple backpack to a nail, and a nail to your kitchen tap. Now let's take one last huge jump and see just how massive this idea of pressure really is. Because it turns out this whole relationship between force and area and height, it doesn't just work on the small stuff around the house. No, it scales up, way up. In fact, it's the engine behind some of the most powerful forces on Earth, like giant thunderstorms and even cyclones. These incredible events are driven by nothing more than differences in pressure, just happening on a massive global scale. And that leaves us with one final mind-bending thought. Just think about this for a second. If just a few feet of water in a pipe can create enough pressure to make your sink work, what happens when you have a column that's not a few feet high, but miles high? And it's not made of water, but of air? Well, that's our atmosphere. And the giant differences in pressure it creates, that's what gives us wind and storms and literally